Okay. So we will have again 45 minutes plus, let's say 40 minutes plus 45 minutes. And the idea here is still, as I said, sorry, Benjamin, I will go here. Now, what we would like to do now, what is the plan now in this 1 hour and a half is basically to derive the propagator for the graviton. So in the same way we derive the propagator for the, for instance, photon in electromagnetism in QED, we want to do this, follow the similar steps and do derive the propagator.
There is a question online again. Can you read it? Otherwise.
How is that? Quick question from previous lecture. At least the operator is defined as the projection of spin operator along the direction of motion of its eigenvalues. And its eigenvalues are ellipses of the particles. How is that definition of definition? No, because so you have lambda, so what is the name? Abhinandan. So the question is basically how is the relation between ellipse and the rotation matrix? The thing is that the ellipse will be the projection of the angular momentum along the direction of the p momentum, okay? And for instance, let's just take if we have, for instance, some momentum that points toward the z direction, what you will do, you will just select the z component of this angular momentum, okay? And when you do that rotation that I showed before in the xy plane, basically we are rotating around the z axis, okay? The eigenvectors of this rotation matrix will be related to exponential of I jz theta. Okay, I call jz lambda, but because jz becomes an invariant in the case of massless particle. And it is the least which is important to classify the particles. Okay, that's the relation. Is this clear? Okay, perfect. Okay, now, as I said, when I go, we would like to compute the propagator and actually try to show most of the step, at least in one gauge, and then we will mention other things in other gauge. But what we will do now, basically, is to start with the covariant gauge, and then we will use non-covariant gauge later, and I think will be instructive for other reasons that we will see. So in the first 40 minutes, which is now I think 36, 37 minutes already, we will derive the graviton propagator in a covariant gauge. And what is the meaning of deriving a graviton propagator? Basically, take the kinetic operator as if you had a scalar field, right? If you have a scalar field with some kinetic operator here, where kappa, where k is box in this case, 1 over box, so the inverse of this operator will be the propagator. But of course, here we have a tensorial index, we have a tensorial object, which is h mu nu. And so this kappa, kinetic term, kinetic operator, will have 4 indices. So we need to invert a 4-index matrix, 4-index operator. And also we have symmetries. So we need to see whether this operator is invertible or not. But anyway, let's call the propagator G mu nu rho sigma. And the propagator will be defined as basically the solution of this equation. Okay, so this product, if G is the inverse of kappa, has to give an identity. But since we are in a space of symmetric tensors with 4 index, the identity will be something is given by this expression, mu rho no sigma plus mu rho. No sigma. No, I don't say. Mu rho, mu sigma, nu rho. Okay. And for convention, I also put an I here. Now, why is this the identity? Because if you act with this object on a tensor with 4 index which is symmetric, you will get the same object. So it is an identity matrix. The same could be written also actually with different order of the indices. For instance, we could write something like this. And then this will be some object of this type. Okay. So we need to ask this question. Can we find a solution for this operator? Actually, if we really take the operator that I showed you before, the kinetic operator for the gravity that is written down there, that operator is not invertible. Just because we have a gauge symmetry in the theory. Why is that? Because there exists, we can find an eigenvector for this operator kappa with 0 eigenvalue. Indeed, if we take a vector of this type, I call it vector because it will be the vector for this for index tensor. If you take this tensor, okay, and we act on this, we get 0. And we know that since we have a set of eigenstate with 0 eigenvalue, then we cannot invert this operator here. This is the same that also happens in the case of QED for the photon propagator, right? Because for the photon propagator, we will have 1/4 f mu f mu. Let's just make a digression here, which is basically what? Which is basically the following: 1/2 a mu eta mu box minus a mu. This is basically the kinetic term for the photon, where f mu is this combination, right? And the same, this operator here, which is the kinetic operator for the photon, is not invertible, because if we call it kappa mu nu, kappa mu nu has always an eigenvector with 0 eigenvalue, which is, for instance, something like this. If we take a vector of this type with a generic function lambda, this is 0. So to invert it, we need to do something. So basically, we have to break the gauge symmetry, the gauge invariance of this action. If you break it, then you will not have any more this eigenvalue that possibly can give you 0 eigenvalue to this matrix. And how to do that? Well, the general prescription is basically take the Einstein-Hilbert action, in this case up to quadratic order, and add a so-called gauge fixing term. For instance, in the case of QED, what would you do? You would add S gauge fixing for the photon, which is something like this, for instance, right? The standard Lorentz gauge fixing with some coefficient here, whatever. Okay, and if you add this term here, of course, you will get a propagate. You will get some object, some new kinetic operator, which is invertible. Actually, let's do it since we are. If you add, for instance, minus 1/c, the 2, I guess, you can write the QED action with a gauge fixing term in this way. So basically, we'll have minus 1/c. A new. Okay, we'll get a new kinetic operator that is invertible. Okay, you invert it, in the end, you will get the photopropagator, which is, for instance, something like this, right? You'll have eta mu nu over p squared plus c minus 1 p nu over p square. Okay, that's what you usually do. Then you can choose your c and fix the type of gauge fixing you want. Okay. But what is important is that basically, thanks to when you go on shell, thanks to conservation law, this part here will never contribute to on-shell amplitudes. So this gauge fixing part in the end will be unphysical for the on-shell physics. So we want to do something similar also for gravity. Okay. We want to do something similar also for gravity. So basically, we have to take the kinetic operator, add a gauge fixing, make the operator inverted, and see what we get. Okay, that's the logic. And as I said, in principle, there are infinite type of gauge fixing you can have. Let's start with the most standard one, which is the Donder gauge fixing. So basically, what we do, we define a new action called S tilde, this quadratic in H, which is basically the quadratic action that we wrote before of Einstein. I just called it S tilde. That depends on eta and H. And then we add a gauge fixing. Okay. Also, in this case, we do this. And the gauge fix we're going to add is so-called gauge fixing the Donder, which is defined this way in my notation. We have this function f mu contracted with another f mu. I'm writing this because one can think of generalizing to more generic background, but it's not needed. Where this function f is given by this expression. Okay. And basically, you have the square of this function in the gauge fixing. And you can see this term is not gauge invariant. So we are breaking basically the gauge invariance of your action. And you can ask, okay, what is now the kinetic term, the full kinetic term that I have? That's why I should have written that. But anyway, so let's now say we have this action. We can do the same. We can write everything in terms of like h mu nu operator h rho sigma, but we will get a new kinetic operator that we call kappa tilde. Okay? What is this kappa tilde? Well, just take this structure, do the same, integrate by parts, identify things, symmetrize, and everything. What we will get is basically this structure. Well, here I erased things. I didn't even notice that. So there is no sigma rho mu, and here there is plus. We'll get basically the same structure that you have also here. This, which is this one, and this one. But you will not touch this one. Okay? So the new kinetic operator, I will write it because it's good to write it fully, is the following. Again, kappa tilde mu nu rho sigma. You will have the same structure as there, eta mu rho nu sigma plus mu sigma nu rho minus 1 over 1 to c eta mu nu eta rho sigma box. So you see the effect of the gauge fixing there once you as I said, integrate by parts, everything, and so on. Then you will have plus 1 minus 1 over c times mu nu rho sigma plus rho sigma derivative mu nu. And you will have another like this, another term of this type also here. And so you have the same structure is there. Now, since people on Zoom cannot see both, it's better if I write it. And it basically is like nu sigma plus mu sigma nu rho. And now plus, I mean, change mu and sigma and nu, okay? Which is the same there. So you see, what you are really doing when you introduce this gauge fixing, you are affecting these terms here. Most importantly, you see, you want to invert an operator now, but when you have just box, it's easy because somehow you have the 1 over box. That's more or less the logic. But if you have uncontracted derivatives, like this one, right, it's more complicated to really invert the operator, the kinetic operator. But in general, what is that you should do? You say, okay, I have my G mu nu rho sigma, which is a propagator. I expand it in a basis. Coefficient Ci Bi mu rho sigma, where this basis basically is all possible combination of eta and the derivative that you can have if you go to momentum space of momentum. So basically, this one will be 5 independent symmetric. Up to symmetrization, you have 5 independent elements in your basis because you have this one, you have this one with mixed index, you will have this one, mu nu, p mu, oh sorry, p rho, p sigma. Then we will have the mixed mu rho p nu p sigma. And then Lorentz invariant also tells that you might have also these type of terms. Why not? Indeed, this form 5 independent terms that you can have. So what you should do in principle is take this propagator, expand in this basis, for instance, with some unknown coefficient, plug this expression inside here, and try to find what are these coefficients. Once you find them, you determine the propagator in a generic de Donder gauge fixing. You can do that, and actually we will see that can be done more easily using the so-called spin projector formalism, but we will do that later. What we will do for now, for the time being, is just let's derive the propagator in the simplest gauge that you can imagine, which is the gauge fixing in which these terms are cancelled. And you see, this can happen when Xi is chosen to be equal to 1. Because if you take Xi equal to 1 in this gauge fixing here, because you have this constant parameter here, you can choose the way you want. If you choose that, you will just get basically a simpler form for kappa tilde, which is simpler to invert. And since having the propagator in the so-called Feynman gauge, I studied something good that will also be needed in another lecture, like for instance, later Anna will use it, either today or tomorrow. It's good to show it complete derivation of it in the Feynman gauge. And what is that? Let's stay here. No, let's go there. I mean, anyway, Zoom people don't see anyway. See if I no. Let's stay here. So as I said, what we will do now, so the logic, I mean, is it clear? What you should do in principle is the following. Take the symmetric tensor with 4 index, expand it in a basis with some unknown coefficients, plug it in the equation you want to solve. This time will be for kappa tilde, because it's the invertible kinetic term, and find the coefficients. Is the logic clear, right? Okay. But you may imagine you have to do so many products and so on. It's like it takes time. It's not even so instructive. Let's just try to find, for the time being, the propagator in the so-called Feynman gauge, which in my notation means T equal to 1, Feynman gauge. Okay, we work with this now. Are there questions? Okay. Here we're doing the simple way of inverting a propagator, of course, to do things more consistent with self-interaction and so on. Want us to add more things in the Lagrangian, but we'll mention something tomorrow. If it's just quadratic level, this is what you're doing. You're adding something that is unphysical on shell, but is useful to basically invert your kinetic operator and give you, in the end, the result for the propagator. Let's work in this gauge, fixing. So basically, C equal to 1. And then you have mu nu rho sigma, right? Actually, let's just go. So you understand, if I set this C equal to 1, you will kill these terms, just because they're proportional to this parenthesis here. And let's just go in momentum space, since we want to compute the propagator in momentum space in the end. So basically, let's rewrite this in momentum space, which means take box and send it in a minus p square. And that's it. Here there is a box, which I forgot. Okay. So basically, in the Feynman gauge, the kinetic operator in momentum space will be something like this. Let me actually call the coefficients A of P. But okay, let's do this. I'm calling with some, because it's useful for now. You have this expression plus a B of P, which is another coefficient, it depends on P, proportional, this combination here. And if you go to momentum space, you see that that A of P is equal to minus 1 over P square. Sorry, 1 minus 1 over 2 times P square. And B of P is equal to the opposite. Okay, so this is the kinetic operator with the Donder Feynman gauge fixing. Now, to solve this equation, we can make a simple ansatz and see whether this ansatz solve the equation or not. So what we can do, we can take a propagator in the Feynman gauge, that's x equal to 1, and we make an ansatz of this type. So we imagine we have some capital A of P, mu rho nu sigma, sorry, these are lower index, mu rho nu sigma plus mu sigma rho nu rho plus some capital B, which is an unknown, we need to find it. Okay, so in principle, this may not be a good ansatz because you plug it in and maybe will generate terms which are not contained in this eta, but will be of this type. In general, can happen that, but in this case, it doesn't. Indeed, this type of equation is closed basically. And indeed, what you have to do basically now, you take this kinetic operator, you take this propagator, this ansatz, you plug it in this equation, you impose that it is equal to the identity, and you derive what are the coefficients A of P and B of P. Okay, this capital A, capital B, because we know already which are the small a, small b. And if we do that, what we will get is the following. So if you do the products between these objects, so if you multiply kappa and G, what we will get basically is like something like we will have 2A times A plus 2B plus A, no, sorry, plus A plus 4B that multiplies mu nu rho sigma. I'm just basically multiplying these two, okay? Plus 2A that multiply this other one. And we get mu rho nu sigma plus mu sigma nu rho. Just do the product, that's what you get between kinetic operator and propagator. And this must be equal, as I said, to I 1 over half eta mu rho nu sigma plus mu sigma nu rho. Okay? When is this equation solved? When basically we impose that 2AA plus 2BA plus 2BB, sorry, 4BB, is equal to 0. And when 2AA is equal to I over 2. Taking these values for A and B, in the end, what we get is that A of P is equal to minus I over 2P squared, and B of P is equal to I over 2P squared. This means that the graviton propagator in the Feynman gauge, the Feynman-de-Donder gauge, is what? Is minus I over 1 over half minus psi p squared, and I also put, to keep in mind of the prescription we use to shift the pole in the complex plane for the propagator, right? The minus psi epsilon. So 1 half this, and then there will be this combination. Eta mu sigma nu rho minus mu nu rho sigma. And this is the Feynman propagator in the Feynman gauge. Okay, you see, we managed to invert the operator, and we got this somehow simple expression. Okay, and this is the thing, one of the most common expressions we usually find for the propagator. So what does that mean? What does that mean? That now we have a propagator, you can compute, for instance, amplitudes. You can say, okay, if I have some vertex, I know what is the propagator, I work in this gauge, I put the propagator there, I put the vertices and I compute scattering. And for instance, some of these scattering processes amplitudes with this propagator will be seen in the lectures by Anna. And maybe they're also in the lectures. Are there questions about this? Yes. Yeah, basically, no, this is, yeah. So you can either work with the tensor with the 2 index up, or the one with the tensor with the index down. In this case, I'm raising and lowering the indices with the eta, with the tensor eta minimum. Okay, so actually this is, let's say, more precise in terms of identity, because you really generalize the delta Dirac concept. Sorry, you really generalize the Kronecker delta to a 4-dimensional to 4 index cases. Okay, but you can equivalently write in this way in this simple case. Ah, sorry, yeah. So basically, our point is made to derive the propagator, and the propagator is defined in different ways, but here the propagator is defined as the inverse of the kinetic operator. Okay. Now, yeah, right. It's clear. Okay. So, it's like when you want to derive the Green function, you say differential operator on Green function equal to delta for the Dirac delta, right? But if you have tensors, you will have indices. If you go to moment to space, you will have this type of relations. So what you're really doing here, you're inverting, you are finding what is the inverse G of this object kappa tilde, where kappa tilde is not the kinetic operator just of the Einstein-Hilbert action, but is Einstein-Hilbert action plus gauge fixing. In this case, we worked in a specific gauge fixing, which is the Feynman gauge fixing. Yeah.
So you're saying potentially this is not closed, you were saying. So does that mean that in this left-hand side you generate?
No, here you don't, this is closed here.
Right. Yes.
Yeah.
But so in cases where it's not.
It may happen that you see, let's suppose that you say, okay, I want to write my propagator as an ansatz in terms of 1, 2, and 3. a combination of these three elements in the basis. But then you multiply it with the kinetic operator for some choice of, whatever. For instance, for whatever, some choice of kinetic operator. It may happen that you generate some term of this type that you didn't put in the ansatz, and so you get an inconsistency. So the system is not closed. You cannot do that. Okay. Yeah. Are there questions about this? Yeah. Yes.
If A equals to minus 1 over p square and B equals to 1 over 2p square, then 2 capital A plus 2d capital A supposed to be 0 already.
Yeah. Wait a second, I wrote it correctly. Let me see. I did it quick. Sorry, this is AB. Okay. Yeah. And this is B. Well, it's the same. No, I think it's correct. Because this is BA, AB, 4AB, 2A play. Yeah, so if you solve this equation equal to 0, which is this one, 2BA, 2AB. Yeah. This is the problem. I wrote A instead of B here. Okay, now it should work. I wrote AA, but AA is the one that is here. Okay. Is it okay now? Yeah. Now, if you solve this equation, you really get this one. Sorry, step. So basically, what you do, you do the product, you generate this, and you say, okay, this structure is the same as the right-hand side, so they must be equal, while the other has to be 0 to have the identity. Yeah, thanks for the question. Okay. Other questions? Okay, good. We are perfectly in time to say many more things.
Line.
Ah.
How did you determine the pole shift prescription? Are we using the scalar field ansatz to get Feynman propagator?
No. So in the beginning of the first part today, I mentioned that most of the, usually we work with the Feynman prescription for the, here we have Feynman that appears many times. So let's not confuse Feynman gauge with Feynman prescription for the propagator. Feynman prescription for the propagator means that in the signature I'm working one, which is minus plus plus plus, you take p square and you send it to p square minus I epsilon. What does that mean? It means basically that if you look at the poles in the complex plane, because this will have a pole, right? There will be pole at p0 equal to plus minus omega p, where omega p is just basically the modulus of the vector p. There will be poles that appear on the real axis. To deal with this singularity on the real axis, when you Fourier transform and you compute integrals and so on, you have to tell how to basically overcome these singularities. And the one that usually uses the Feynman prescription will tell you that if you have the complex plane in P0, and you have poles here and here, you shift one pole here and one pole there. That's the Feynman prescription. Now, does this come from scalar field and so on? Well, it doesn't matter the tensor structure, because you may forget about the tensor here, and you see the pole does not depend on whatever tensor structure you have. The pole singularity is independent of this tensor structure, which is just there to make it tensorial. But what is really important for the pole part is this scalar contribution, which is it's the same as if you had a scalar field. Okay. So we just say, let's use the same tools that we usually use for all the interactions, which means Feynman prescription. And this one sometimes is called causal prescription because it tells you, that positive energy propagates forward in time, if you analyze it. But yeah, is this clear? So the tensor structure is not really important for the prescription in the bottom of the propagator, in the denominator. Avinandan, is it clear? Yeah, okay, good. Okay, so if there are more questions on this, I would like to say some more things on the propagator, which I think is, for me at least, was useful to learn. Yeah, let's go here. Okay. Now you see, is the time? Sorry. Okay, let me just tell you something. Now you see, we did an analysis of degrees of freedom, and we found that basically, in the end, we expect only 2 physical degrees of freedom to be the propagating ones. Okay, but if you look at the propagator now in the Feynman gauge, of course we have many components, right? And since we are working a covariant gauge, it's not really clear which of these, which are the components that are physical, that will really carry some whole 1 over p squared, and which are the components that instead, in the end, they will not carry any pole p square on shell. Okay, I will try to be more clear in a moment. But in general, what you should expect is that in the end, the physical components of the propagator that will have a pole at 1 over p squared, the physical on shell component have to be 2. Okay, but you see, if you write that expression, you will have G0, 0, 0 in the Feynman gauge, which is what? It's 1 over 2 minus p squared. Let's forget now the I epsilon, right? You may have G1, 1, 1, 1, which is again the same. Then you have the same for 2. And you get again the same. So already here you see that you have 3 components with a pole, but in general, how can we understand which are the physical components of the propagator? The one that really in the end would matter in the on-shell propagation. Yes, Gabriel. Yes, but you have twice the Minkowski. So it's minus time minus 1, minus square. Right, because I'm taking 0, 0, 0, 0, 0, 0. So, okay. So it's the same thing when we say that if you have a theory that is written in a gauge invariant way, why we write QED in gauge invariant way usually? Because we would like to keep relativistic invariance, but we know that we are hiding the physical degrees of freedom. But if you work in a non-covariant gauge, actually it's very nice because you can make it the degrees of freedom. You can make the degrees of freedom that are the propagating one physically on shell explicit. Now it would be nice to do something similar also for gravity. And so this is one of the main points that we don't see. I mean, you see, if you just work in a covariant gauge, okay, it's not clear which are the not clear okay, physical dots. They are not clear which are the physical degrees of freedom or the physical components. Physical on-shell components of the propagator. Let me be more explicit. Basically, if you compute the residue of this propagator, which means you multiply by p squared, you take the limit for p squared going to 0, okay, you will get something, okay, but what are the on-shell, the component that really on-shell, because you're taking this p squared going to 0, really survive, okay? Here it's not clear at all, because they are not, it's not clear how many they are independent or not. As I said, here you already get 3, but some of them is not really there on shell once you really scrutinize everything, okay? And there is actually a nice way to understand what is happening and how to really identify the physical component by working in a non-covariant gauge fixing. Non-covariant, my gosh, covariant gauge fixing. Which is basically the following. You take GF as before minus C. Therefore, X, again, F mu, where now F mu is not anymore the under one, but is the following. Okay? And in particular, we will work in the gauge fixing that is non-covariant in this limit. So we compute the propagator, we take this limit, and we see what happens. And this is so-called Rentke gauge in gravity. To be honest, when I read this name, I said, who is this guy? And I couldn't find the reference to this work, but in the paper by Toft and Beltman, this gauge is called Rentke. But I don't know what is the reference. But anyway, I think it's very interesting to work in this gauge to see something beautiful about degrees of freedom. So this problem of physical on-shell component, to understand what they are, can be really make it clear with this gauge fixing. Second, there is another problem, I would say, with this type of writing the propagator, because, okay, these are the on-shell degrees of freedom. But off-shell, you can still ask, before going on-shell, what is the spin structure of your propagator? Because you see, in general, you have an h mu nu, which has tech components. But under SO3 rotation, you can make a transformation and see how the components transform. And you can always decompose them in terms of a scalar, another scalar, a vector, and a tensor. So you will have 1 plus 1 plus 3 plus 5 equal to 10 components. Okay? Now we know that on shell, in the end, only the transverse traceless part of the spin 2 will propagate. But off shell, before going on shell, there may be some component which actually participate in virtual processes in a diagram, for instance, which is not just the spin 2, there could be also a spin 0, spin 1, and so on. Some of them maybe will be gauge fix independent, some of them will not, whatever. So the idea is that this type of spin structure of the propagator is not evident in this way of writing it. It can be made explicit by using the so-called spin projector formalism, which will be also useful for something we will say in the last lecture tomorrow. Because basically you can rewrite the propagator in terms of the spin component, that are propagating inside it in a very explicit way. Okay, so you see, we derive the propagator in the Feynman gauge, but there are things which are not very clear a priori. Of course, you can always make it clear by working harder, but in my opinion, it's very nice and instructive to see these two things: how to make the number of degrees of freedom that physically propagate on shell manifest in the propagator, and also how to make manifest the spin structure of the off-shell components that are in the propagator. So we're going to do these two things, and then we will be done more or less with the free theory up to another thing that I will say. Now is 44. Is a good time to stop for 2 minutes for question if someone has to go to the toilet. Yes. Okay. So the question is why we can decompose h mu nu in this way under rotation. So what I mean with rotation is that you really take some matrix that I showed before, you make rotation. I mean, you do some rotation. The group SO3 will be a subgroup of Lorentz and whatever. And more generically, you can write a rotation in this way. You may say that I go to x naught prime to x naught. You don't change the time, but you change space. So you will have some x vector prime equal to some function of fx vector, right? This is basically a general way to write a rotation. So you say, if I do this transformation How do the components of this H mu transform? Or if I do this transformation, which are the components that mix among themselves? Because if there is like a subgroup of components that do not mix when you do this transformation, then you will have a irreducible part of your representation of the SO3. Okay? And actually, under SO3, you can decompose it in 1, 2, 3, 4 blocks that are irreducible, which means that you will have the trace of H, the H00, the HI0I, and the HIJ, which basically, under rotation, will not talk to each other. And let's see, for instance, some cases. Okay, now, for instance, if you say we want to go to, okay, we have in general, you have a tensor with indices. If you do some Gaussian transformation, they will transform in some way, right? If you have contravariant tensor, they transform in some way. If you have contravariant tensor, if you have covariant tensor, they transform in another way. So you will have some partial derivative of x, right? And here you will have some h rho sigma. So you go from an h prime to an h. That is transformation of rotation. In this case, is a rotation. Boop. And let's suppose here we have x prime, and here we have x. Well, let's see if I remember. Yeah, if we do that. Let's suppose you do this transformation, okay? And you want to see how things transform, okay? Now, if you take the 0, 0 component, what you will have is basically, so you will have some time here, okay? And we know that when you have time, they will only give non-zero if they act on x naught, otherwise this is time independent, okay? So basically what you will get, basically this is 0, unless rho is 0, so you will get something like rho 0, okay? Then you will have the same for the derivative, which is sigma 0, h rho sigma, okay? So basically, you see, h00 prime goes in h00 and does not mix with the other components. So this is somehow an irreducible part of it. You can do the same for the trace, for the h0i. The h0i will transform as a vector, and the hij will transform as a tensor. Okay? And you can do the same also for the vectors, right? If you have a vector, you can decompose it like in a spin 0 part and a spin 1 part. And the rotation, this is a scalar, this is a vector. Okay, so this is the story. And the idea is that actually you can introduce in your propagator for each component a spin projector, which tells you that my propagator will propagate off shell at least, a spin 1, a spin 2, spin 0, and so on. You can make it explicit. Okay, and that's nice that it can be done in this formalism called spin projector formalism. Is it clear? Okay. Are there more questions? Yes. Yeah, we'll do it now, actually. We'll use that, but you can ask. Yes. But since, in the end, gauge fixing do not affect your physics, on-shell physics especially, whatever you put there is fine. It's like when you work, for instance, in QED, and you impose not a Lorentz gauge. This is the gauge fixing of, you can do the same for QED. Let's suppose you just want to work in terms of gauge condition, no fixing. This is a covalent gauge, right? That you impose in QED is fine, but you can also impose something like this, which is a Lorentz breaking condition, of course. right? Now, the spirit is similar, but not completely, because here, see, it's something, yes, it's something non-covariant, but we work in a specific gauge, which is the limit C equal to 0 is taken after computing propagator, and is called the Prentke gauge. Prentke gauge. So it's fine. You can break, of course, Lorentz, but you can even write QED Lagrangian in a non-Lorentz invariant way by making explicit the nature of the physical degrees of freedom. So you write it in a gauge invariant way just because you want to preserve somehow the relativistic form of your Lagrangian. But in principle, if you're crazy enough, you can just work with non-covariant. Covariant gauges and work with the degrees of freedom explicitly. But I guess in this case, computation will become become harder in most of the cases, especially of scattering amplitudes. Yeah. Okay. Okay. Yeah. Okay. It's time to go on. In this for 39 minutes, we'll try to address this question. Of course, we will not go spin structure, we said. Oh, propagator. Of course, we cannot go in many details because there is no time, and also is not in the end needed. They are in the lecture notes, everything, all the details. But let me tell you these 2 points. Let's address this point. First, let's make the propagator. Let's compute the propagator in that gauge, which is non-covariant, and then take the limit. So we go in the Prentke gauge. And let's show that what we get, that the only poles are 2, okay? At p squared equal to 0. Yeah, okay. So let's do it here. So we work with the, we said this gauge. Now, yeah. What you can do first, of course, is to write everything again in a quadratic form. Is always the same logic. You will have a gauge fixing with this, and you can write something like this. Okay. How can you do that? Again, you take this action with this covariant, non-covariant gauge fixing here. You integrate by part everything, and you will get basically something. Okay. Let's just write in momentum space how the kinetic operator reads in this gauge fixing, with this gauge fixing. In momentum space, we'll have the following. Again, I wrote this already 1,000 times. We write it 1,001. Okay, this one, p square, then there is again. Square. This does not get affected by the gauge fixing. We just have this one plus. And what gets affected by this gauge fixing is actually the last term. So of course, yeah, this was the donor gauge. Let's forget about the donor gauge. We are just writing the gauge fixing action now for this new non-covariant term. So we can erase this. And what is this? Will be the following, plus 1/2, and there is this structure. P nu P sigma minus 1 over C, and I'm defining this P bar nu P bar sigma. P bar basically is the following object with 0 temporal component. And then you will have the same combination as usual, but that's what basically the gauge fixing here changes, this part. sigma. Oof. P rho P nu. And again, 1 minus C, P bar rho P bar nu. And let me not write it. Yeah, let's go fast. So we need to change then mu and nu. Okay. This is the propagator, sorry, the kinetic operator in the with this gauge fixing here, where this P mu, as I said, is defined this way. Okay. Now, what is the idea? The idea, of course, I mean, we want to invert this object, and you see, it's not like in the Donda gauge that we can simplify things just by choosing axi and killing the non-contracted momenta. No, we cannot happen just because you don't have covariance. You cannot achieve that, at least in this case. So we need to do something else. And actually, there is a nice way to derive the propagator, which is difficult to write on a blackboard, on a whiteboard, but the logic is the following. First, as before, let's just work. Let's assume that the momentum is along the z direction only, so we can rotate the momentum. So we will have P mu like P0, 0, 0, P3. And then P bar that I defined down there will be 0, 0, 0, P3. That's it. And what you can do now, basically, you can write down, of course, you can check which are the components of this kappa tilde, this kinetic term, this kinetic operator, that survive. There are many of them. But you want to invert it, okay? So there is a nice way to invert it, which is the following. In the notes, you can find all the details. So basically, first, you define a vector h hat, which is 10-dimensional, so it has 10 components. H00, H01, H02, H03, H11, H12, H13, H22, H23, H33. Yeah? This is a vector with these components. Then what we do, we define a matrix, 10 by 10 matrix, Ij, which is equal to some coefficient Sij, I'm calling it with this parenthesis, kappa tilde Ij. What I mean with this parenthesis Ij? That I and j can take only 10 values. Which are these 10 values? Well, basically, is this list. So this is I equal to 1 will be 0, 0. Okay, it's a way to write basically a four index matrix in terms of a 2-index matrix, but we go to 10 by 10 in this way. And then you see, I mean, we do 1, 1, 1, 2, 0, 3, 1, 1, 1, 2, 1, 3, 2, 2, 2, 3, 3, 3. Okay, so you see, now you have what? These are symmetry coefficients because you see, you will have like kappa 0, 1 or 1, 0 and so on. So I mean, these components will appear more times, basically. But the point is that you can write the action in this form now. Is the same as this one. You can just write it in an equivalent form, which is matrix form. You have a vector H hat, hat. You have this matrix hat, and then you have the transpose of this vector. So these two are completely equal. This is a tilde, and this is equal to this one. There is no difference. I'm just writing it in a different way, funny way. Okay. But why this is useful? Because now you have a matrix, which is this kappa hat, which can be inverted as a normal matrix because it has only two indices, two indices, but they are 10 by 10. So of course I cannot write it because it would be huge, but it's written in the notes actually. You can find it. But the logic is the following. It was before, we are inverting a kinetic operator. We're just finding a smart way to invert it. Okay, because this is smart, because in the end we are all interested in understanding which are the whole p square part, the 1 over p square part, 1 over p square part that propagates when you go on shell. So you write it in this way, and then you ask, let's invert now this operator. It will be a 10 by 10 matrix. If we invert it, we'll get another 10 by 10 matrix, which will be the propagator written in this matrix form. Okay? And what we will get in the end basically. So we say we want to find, we want to solve this equation, where this is now the identity of a matrix 10 by 10. Okay? Just simple matrix operation. We just want to invert this object. Now, since we have imposed a gauge fixing, we have put a gauge fix, we can invert it. And actually, in the notes, you can find just the expression of G, like 10 by 10 matrix, given this frame in which you have only P3 as a spatial component. Then, of course, I'm not going to write it. But then, what is the logic? We go in the Prandtl gauge, which is this one. We take this Xc equal to 0, where the Xc is the gauge parameter that is here in the gauge fixing. Okay, like we did with the quantum gauge, we chose Xc at some point. Let's choose it. And in the end, we will get lots of simplification because lots of terms will go to 0. But still is a 10 by 10 matrix. But if we just focus on the subspace, let's call it sub, of the indices ij of this operator here that run in this set of possibilities, right? 10 indices, the 10 different values. If we focus on the subspace of these indices, that is basically 1, 1, 1, 2, 2, 2. So basically just focus on a 3 by 3 matrix. You will see that. What you will get is the following: sub equal to a 3 by 3 matrix, as I said, which is 2 over p square. No. Minus 1 over 2p square, minus 1 over 2p square, minus 1 over 2p square, 0, 1 over p square, 2, 1, 2p square, 0, 0, 0. Yeah. So basically, this part of the propagator is the only part that contains 1 over p square poles. The other components will only have 1 over p3. There will be no p square that appear anywhere else. Okay? So this is the only part that contains p square. Now, you can ask, still you have many components here, but how can we determine really if there are independent components, or which are the independent components? Well, we can just compute the eigenvalues of this matrix. And if you compute the eigenvalues, basically just solve this equation, G minus lambda identity sub equal to 0. What you will find out that the eigenvalues lambda, let's call them, lambda, is 1 is 0. The other one is 1 minus 2p square I. And, well, yeah. We don't need to put I. I'm forgetting the I for now. 1 over 2p square. And lambda, so lambda 1, lambda 2, lambda 3, equal to what? Equal to 1 minus p square. So, to recap, we inverted the matrix. We got the propagator, which will be a 10 by 10 matrix in this formalism we are using to invert it. Then we take the Prandtl gauge, which is this limit in the gauge fixing. We will get this time by time matrix of the propagator, which will have many components that are 0, some of them that are not 0, but they have only 1 over p3 square, so it's not a pole on shell. And then there will be a part of it, which is this subspace of the matrix, that contains poles. But many, you can ask which are the physical ones, which are the independent ones. If you diagonalize it and you compute the eigenvalues, these are the only 2. And what happens? That in the end, we found only 2 independent poles, which is consistent with the fact that we have only 2 degrees of freedom on shell and jar. And actually, what is nice is that in the Prandtl gauge, which is this one, you can write, it's easy to do that, we will find in the notes, the propagator you can write the propagator in the following way. There will be minus I over 2, 1 over p square, and for completeness also put the standard prescription here. And then here you will have this type of structure. Let me introduce this object, delta bar, which is nice. Plus something. And this delta bar, basically, is just a diagonal matrix 0, 1, 1, 0. Okay? Basically, what happens here is that in the Prandtl gauge, you can write your propagator in the following form, where you have this delta bar now appearing, which is not the eta, which only work in this subspace. And what are the other terms here? Well, these are only terms proportional to 1 over p3 square. So this part that is not writing here, it's not written here, that I'm not writing anymore, does not contain any pole at p square. So basically, in this non-covariant gauge, it's nice because you can really get the propagator in this very explicit form, which is of course non-covariant, but it's telling you that you just have 2 independent components that carry 1 over p square pole. Not only that, what you can show is that this structure here that I wrote there sigma minus bar rho sigma. What is this? This is nothing but the sum of these 2 terms. You remember before we defined E plus and E cross. You can show that basically this is equal to this cross. And this is just telling you that indeed this tensor structure in the propagator, which contains only the physical on-shell part, will be proportional to the polarization of the tensor, which will decompose your propagator, basically, but only the independent ones. And indeed, if you go on shell, which means you take this residue, right, in the Prandtl gauge, what you will get is only this part. So what you will get is minus I p square p rho sigma plus cross no cross. Okay, this is the on-shell propagator that has only 2 poles at p square, nothing more. And this is, I think, very instructive because it somehow shows you that if you work in a non-covariant gauge, somehow you can explicitly see which are the independent components. And why is this also useful? As we'll mention tomorrow if there is time. that usually, in quantum theory, we have to introduce also, when you have especially gravity, we introduce something else in the Lagrangian, which are the Faddeev Popov ghost. And these Faddeev Popov ghost fields, they should not propagate on shell. But in covariant gauge, it's not very clear if you just look at the propagator. If you go in this covariant gauge, non-covariant gauge fixing, you will see that the Faddeev Popov ghost propagator has no pole at all. That's why it cannot propagate on shell. Okay, so I hope this part, of course, I skipped the computation of the 10 by 10 matrix, which there is no way to write it, and it's not even instructive, but you can find the notes, in the notes, everything. I will give the notes, hopefully, by this week, in the next days, let's see. But please, I hope this consideration on the non-covariant gauge is clear, but if not, ask questions. But I forgot to check the time. Oh, you have 20 minutes. Okay. Good. And I mean, to be honest, I learned about this type of gauge while preparing the lectures. Yes. The presence of poles? Yeah, so basically, it's the similarity. So if you start from a Lagrangian that is written in a covariant form, that is written in a covariant way, it's difficult to really understand which are the physical degrees of freedom. To understand it, what you have to do sometime, at least to see it explicitly, is to break covariance, introducing, for instance, some Coulomb gauge in the photon case, okay? Here, it's the same. This fact that basically the degrees of freedom, the true degrees of freedom on shell are hidden somehow due to this relativistic way of writing things, is also true not only at the level of the Lagrangian, but also at the level of the propagator. And did you see that? Because if you compute the Feynman propagator that is there, up there, that is not clear which are the components that are really independent. Because it looks like we have many components with 1 over p squared. There is a simple way to understand which are they, and this way of introducing basically a non-covariant gauge fixing. And once you introduce the non-covariant gauge fixing, then you follow the same procedure. Compute the kinetic operator. Invert it. For simplicity, choose one value of the gauge fixing parameter. I'm choosing c equal to 0, in this case, which is called the so-called Prentke gauge. And in that gauge, explicitly, what you get is that the propagator looks like this. The only pole at p squared is this part. Whatever it is left that does not belong to this subspace, because it's 10 by 10, I'm just focused. So this subspace is this, okay? But there is a lot more in this matrix, which is contained here, and other things are here but are 0, okay? Which do not contain any pole 1 over p squared. So if you want to go on shell, for instance, which means you just compute the residue, multiply by p squared, and then take the limit, the only piece that will survive in the propagator is this one. This one will go to 0. And this part actually is very nice because you can write it in terms of product of the independent polarization tensor that we showed before. Okay, which is just telling you that on shell we are propagating only 2 degrees of freedom with 2 poles at p squared equal to 0. Is it clear? Yeah. And as I said, this is very nice because with this gauge It died. Yeah. Okay. Yes. Yeah. Voila. Yes. What is nice about, I think, non-covariant gauges, not to do computation, but to prove statements sometime. Because if a non-shell statement is gauge independent, you prove it in one gauge fixing, in one gauge, then it will be true for any other gauge. Okay? So that's why I think it's nice to work sometime on non-covariant gauges. And one example, I think, is the fact that the propagator, the Faddeev Popov fields. Tomorrow, I hope I will mention something. In the notes, it's written. Actually, no, it's not written yet. It will be written. So yeah, if you want to do computation of amplitudes, I think, I don't know if there are people who use non-covariant gauges of this type for gravity. I guess no one. Especially if you want to evaluate like loop divergence, is even worse because you may generate contact terms which are non-covariant. You have to deal with them. I don't know. Okay. Good. We have 14 minutes. Let's see. So I hope this was clear. You have a question? Please. Yes.
No, it's just thinking about the gauge. If you, for example, in the curved spacetimes, like for example, people use radial gauge in the, for example, when you expand graviton in the spherical harmonics. I'm wondering if this kind of gauge will be useful in the fluid conditions.
I don't know. Yeah, I don't know. I never seen use this gauge actually anywhere. Only actually I found this only in a paper by Beltman and Goft. And actually they mention Prentke, but I don't know, they don't mention any reference. So maybe you know Paolo who is Prentke, who Prentke is. No, okay. Anyway, he looks like someone who in some paper used this gauge. But yeah, I didn't find any reference. But I don't know if this can be useful for other situations. I mean, I think it's very useless for doing computations like amplitudes, but it's nice to see at least structures and prove some statement. Okay.
Are there other gauges that are useful for computations?
Yeah, I think there are many. So for instance, even the covariant gauges that is sometimes often, I mean, very often is useful to work with even more generic gauges, because you see, so far I only introduced one gauge fixing parameter, but in principle you could say, let's write even covariant, an action of this type. An action of this type. And then you take, for instance, F mu similar to the Donder, but with some more freedom. Like this. For instance, you put another coefficient here, another parameter. And this is even more generic than the Donder. Okay, sometimes this is useful because maybe in computation, also, if you deviate from Minkowski background, you go to Kurt's backgrounds. It's useful to have more parameters in order to kill more like some type of uncontracted derivatives you want to kill or whatever. Okay, but so there are many type of gauges you can write down. Okay, you can make it as complicated as you want. I read in the covariant case. Okay, another one could just be take omega equal to 0. Just work with this, which would be similar to the covariant one, but similar to the non-covariant one, but with another 0,0 component is added. Okay, so there is lots of. But what is important is that in the end, the shell physics will not be affected by the gauge fixing.
But in general, you need to, if you have a pole, when you factorize a pole, you have only two components. And you can work with a covariant propagator and impose gauge invariance on the gauge invariance help you to get only two components.
So basically, you just divide the part that is non-gauge invariant, the part that is gauge invariant, and you work, impose, yeah.
You impose the gauge invariance on the object on which you have the amplitude on which you have graviton into n particle, and then the graviton n particle. These are gauge invariant.
Oh, sure.
And so all the components are eliminated except the two physics.
Yeah, sure, indeed. Let me mention also this, because there was something that we mentioned at the end of what I'm going to say about spin projectors. In the end, there is not much time, but so what related to what Paolo said, which I think is the same, correct me if I'm wrong, Paolo. In the end, you see, even if you take the Feynman propagator and you have some stress energy tensor, like you have some amplitude, okay, for some matter coupled to gravity, whatever. And you will compute some amplitude of this type, okay, with some propagator and two different propagators, okay. Once you take into account of the gauge invariance of the theory, which means that you will have, for instance, something of this type, you will have some other constraint comes. What will come out of this amplitude on shell will only be a combination of the physical components of your propagator, even if you start from Feynman. Yeah, of course. Factorize, yeah.
Only two.
Yeah, yeah, yes. And yeah, this is actually that can be done. Actually, you can also, it's also nice to see in this case, if you just keep everything virtual, you don't go on shell, you do this contraction of an amplitude, which are the components that survive. And in that case, you will have not only 2, but you will have 6 for the graviton, because there will be a spin 2, which with 5 components, and a spin 0 with 1 component. So in total, there will be 6 components. But when you go on shell, the 0th component of the scalar part will cancel the 0 component of the spin 2, and plus minus 1 of the spin 2 also will go away because of gauge invariance. You will always be left with plus 2 and minus 2 once you contract it. Then you go on shell, yes. I would say this is a nice way to see the on shell one without even contracting and computing an amplitude. Yeah. Okay, well, I mean, there is a lot, not so much time, but let's say something because in this microphone is. No, I hope it's clear for. Okay, 8 minutes. Well, let's see. I just want to mention quickly something. Maybe, yeah, I never managed to. Let's do something. Let's do what I want. I mean, there is something I want to mention, but let's do it for QED, and then I will tell you the result. In the notes will be written also, just to understand what I mean, because there are many indices here and it's complicated. So as I said before, right? H mu nu can be decomposed under SO3 in this way. So in principle, you can expect the propagator to be written in terms of like, there will be, let's call it a spin 0 projector here. There will be another projector, let me call it this, I call this spin 0 projector, that if it acts on this H mu nu, it will only give me the trace. Then I define another operator that if it acts on G mu nu, will give me only the 0, 0. Then I define another operator, I call it 1, that if it acts on H mu nu will give me the spin 1, vector pan, which is this one. And then I define this other operator, spin 2, will be related to Hij. Now, to be more detailed, but the point is that I would like to write the propagator in terms of these spin projectors of shell. So you can really identify what are the spin component of the propagator of shell. Then, of course, when you go on shell, you know what you should expect. And indeed, as I said before, if you keep off shell and you forget about gauge fixing, up to gauge fixing, you will have only two. You will have 2 component, which is a spin 2 and spin 0. So sometimes people say off shell, the graviton has 6 degrees of freedom for dimension because you will have spin 2 and spin S, which is different from a massive graviton, for instance, because in massive graviton, you only have the spin 2, 5, that's it. While in gravity, massless, you have also the spin 0. Now, the idea is to basically write it in terms of these operators, like some combination. Let me take a little of this, okay? This can be done. But unfortunately, tomorrow I may maybe say something more, but we'll just take maybe 10 minutes more. Let me just say maybe what happens with the QED, just to understand the logic, because you can do something similar for QED, but in QED we'll have less tensorial structure. So In QED, what do you have? You have a Lagrangian. Let me just go to momentum space, which is simpler, which is actually what we want. P square P mu P nu. Right? This is basically Lagrangian here. And you would like to basically introduce some spin projectors for the A mu that allow you to write the kinetic operator in terms of its spin components. Why? Because under SO3, A mu can be written like a scalar and a vector. For instance, sometimes you can write, let's call this T plus more or less something like this. But so you can write it as a scalar and a vector, which means we could in principle introduce a spin projector that projects on the 0 component, which is the scalar 1, and the spin projector that projects on the spin 1 component. And this can be done by introducing two projectors. And projectors usually they form a complete set. So basically, we introduce two projectors whose sum will be the identity, which is just a metric tensor, or written differently. This one. Okay, you want some projector of this type. And they can be introduced. They are this one. This is one. And then you have the other. This is the spin 1 projector. And this is the spin 0 projector. And why you can check that there's spin 1 and spin 0? Because if you act with the trace, you will select the rank of this operator since they are independent. Because if you take pi squared is equal to 1 and they are projectors, right? And orthogonal as well. Okay, just contract indices. What happens that the trace of this is basically given by 3, which can be written as 2 times 1 plus 1. And if you remember angular momentum, this will give you the dimension of the, yeah.
Aren't they square the projectors themselves?
Yes. Yes, they are important, yeah. Sorry, voila. And this means will be a spin 1. And then the same for the other. If you do that, what we get is 1, which is equal to 2 times 0 plus 1, which is basically spin 0. And spin 0. And what is nice actually is that you can rewrite this object in terms of this projector, because the kinetic operator for the photon, what will basically be p squared times theta mu nu minus omega mu nu. That's the kinetic operator for the photon. Okay? So it's written in terms of spin 1 and spin 0. Now, if you introduce the gauge fixing, which I showed you before, I'm almost done. Then we'll leave it for tomorrow, the rest. The gauge fixing, which is, for instance, the Lorentz gauge fixing. In this way, with a plus, what you will get is that the gauge fixed kinetic operator that we call always, the kinetic operator with the gauge fixing that we call always p squared will be, there's a minus what? Theta, there are only two indices for photon, nu plus 1 minus 1 over c omega mu nu. So you can write basically the kinetic operator for the photon with the gauge fixing in terms of these spin projectors. And I use it very easy because you can compute the propagator very easily, because then the propagator for the photon will be g mu nu some combination of A times some coefficient A times this plus B times this, right? You multiply by this, you impose that has to be identity because you want to invert it. But using this relation, it's very easy to invert now. You don't need to go crazy with indices. It's just you know that this is the square is theta, the square is omega, and the product of theta and omega is 0. And what you get for the propagator, if you do that for this coefficient, is the following form: theta mu nu over p square plus xc omega mu nu over p square. And you see that you have in the photon propagator, you can now really identify the structure, the spin structure, which is basically the spin 1, which has 3 components, and the spin 0 that has 1 component, so 4 components. That should as it should be, because you should have all the 4 components in the full propagator. Only when you go on shell, what happens that, first of all, there is one gauge. So you have gauge condition plus residual, right? It's similar here. You will have one that depends on the gauge fixing. That is not physical on shell, because basically when you contrast this with some gauge invariant, with some current, this will give 0 because P mu current P mu will be 0. But then inside here, there are 3 components. Okay, so you would say that my off-shell photon has 3 components. But when I go on shell, I can impose some residual gauge, and in the end, I will only end up with the 2 physical components, which are the on-shell one. Okay, that's what is happening. And actually, the spin structure is very nice and clear in this formalism. Now, unfortunately, there is no time, but the idea is to do the same tomorrow, very quickly in 10 minutes, we'll mention something, for the graviton propagator. Okay, and write the graviton propagator in a similar way in terms of now 4 spin projectors. Okay, and actually this is very nice because it will allow us to make a computation, for instance, of the in the denoder gauge without choosing any gauge fixing parameter equal to 1, just keep it in free. Will allow us to do it very easily because we can use this type of orthogonality and idempotency relations. And then you just multiply and you compute the propagator. And we will do that tomorrow. I hope that the logic is clear for QED, because tomorrow we'll just follow the same in the first 10 minutes, and we'll write down the propagator for the graviton in a generic covariant gauge fixing a la the Donder. Okay. I'm sorry, I think I took 2 minutes more. But I think it's time to stop and go for lunch. If there are questions, please ask. Huh? Yeah, sorry, we have the gong show. Yes. And I guess I need my laptop.